Hello everyone. Good morning, good afternoon, good evening, depending on where you are. Thank you for attending this telecom seminar, which is hosted by Technology Innovation Institute in Abu Dhabi. I'm Dr. Daniel da Costa, currently a principal researcher at TII. For today, I'm pleased to welcome Dr. Walid Saad from Virginia Tech as the speaker of our telecom seminar. The title of his talk will be While Extended Reality over 6G Terahertz Systems, a tale for 2 hours in S. In a nutshell, basically, Dr. Saad will try to explore the potential of using 6G networks at the terahertz bands for meeting the high rate and ultra reliability and low latency communications requirements needed in extended reality applications. Well, I'm confident that most of you know Dr. Saad very well. He has contributed to our community in many ways, not only through his strong publication record. He has been awarded many times due to his great achievements. In particular, he's a AAA fellow. If I'm not wrong, I think he was elevated to a AAA fellow with less than 40 years old, which is not common in our society. And he is also author and co-author of 10 conference best paper awards. He's the recipient of 2015 Fred HRLLC Prize from AAA Communication Society, the 2017 AAA Consoc Best Young Professional in Academia Award, and 2018 AAA Consoc Radio Communications Committee Early Achievement Award, and 2019 AAA Consoc Communication Theory Technical Committee. He was also a co-author of 2019 AAA Communication Society Young Author Best Paper, and 2021 AAA Consoc Young Best Paper Award. Well, Walid, thank you very much for accepting our invitation. And without further ado, the floor is yours.
Thank you, Daniel. And I'd like to thank everybody at TII for the invitation today. So today, I'm going to delve into the use of 6G, particularly terahertz systems, to provide three key requirements for wireless extended reliability. One is rate. This is the first R. Second is reliability. This is the second R. And the third requirement is sensing, which is the S that will come together to allow us to create, if you wanted, metaverse or a wireless extended reality, essentially, over 6G. So first, a quick overview. I think many of you know the terminology, just to be kind of get things started. So extended reality is essentially this look at this spectrum of reality virtuality continuum, if you wish, where on the one hand, or on one extreme, you have someone who is completely immersed in a virtual world, and that's what we call virtual reality. On the other extreme, you have actual reality, and close to it, you have augmented reality, where you have some virtual entities like, a bird, a tree, that are kind of appended on top of reality. And there's also this mixed reality in the middle. So extended reality is a term that many in our community and others are using to kind of look at this whole spectrum of users. And of course, the use of XR, or again, now we call it the metaverse, if you wish, is essentially to kind of integrate these virtual components into this large-scale world that we're living in, right? And it is essential to actually have wireless systems supporting this virtual system. And you can see that there are many applications that could be concurrently done. Like you'd have people visiting a VR-enabled theme park or attending a concert remotely. Others that are actually attending a sport event remotely. Others are using these technologies to just meet among each other, and you could have them at different locations. So you can see multiple technologies come into play here. They start from edge computing at the lower level, if you wish, where you have to start doing some processing at your edge of the network. And then there's all this interconnected wireless communication infrastructure that includes, of course, Wi-Fi, but most importantly, cellular as well, because it is a system approach, right? So a system perspective. So the first question you would ask, well, yeah, sure, extended reality is interesting. There's going to be wireless applications. So why not use why not use 5G, right? 5G can support mobile augmented reality and potentially fully immersive VR, right? And everything in between. So the point being, of course, I'm sure everybody agrees that LTE could do something what we call pre-VR in some sense, and it's kind of the very basic system, which we don't use that much anymore. And at 5G, you can actually do what we can call advanced VR, right? Where you can have maybe even up to 1 gigabit per second of the downlink. And that does enable a lot of interesting applications. But if you think about fully immersive, complete metaverse and complete merger of the physical and virtual worlds, and what I guess Huawei used to call ultimate VR, then you need more than this, right? Then you need actually to transmit the perceptual and haptic requirements, right? So at some sense, Ericsson has already talked about this internet of senses, right? You can send your senses. And to do that, you really need much higher rates. So just to give you an idea, I mean, an uncompressed bitrate of about around 2000 gigabit per second is needed for this. Of course, you can do some compression and improve, but it just gives you a flavor or where we're going at, right? So this means that even with 5G and millimeter wave to some sort, I mean, the lower end of millimeter wave, you probably cannot do that. So we do need something beyond, basically terahertz, and 6G in the sense here in two senses. In one sense, meaning you have terahertz, so new spectrum. In another sense, at the end, I will talk more about sensing, which is an important factor that should be done by 6G systems. So think about these wireless services. If you think about 5G, we always look at this plane of reliability, rate, and latency. So HRLLC, which are very popular, they are really very high reliability, very low latency, but they don't care about rate, right? And MBB or AMBB, they really care about rates, but they don't care too much about latency and reliability. But you can think of all sorts of combinations like this purple one here, which is kind of mobile broadband, reliable low latency communication, where you probably don't need ultra reliable. It's not really IoT, but you really need high rates, but you still need low latency and you need reasonably high reliability. Like in such a regime, classical 5G services may not work well. And in some sense, this is where XR will likely lie. It will likely lie somewhere around here. So when I say XR here in the broad sense, I'm going to focus on VR, but actually what we do does apply to any one of them. I mean, to VR or MR. AR is a little bit different in the metrics as well. So terahertz allows you to have this fellowship of communication and sensing. And you can, I mean, go, if you want a more like tutorial-like material, you can go to our recently accepted comms paper, where we looked essentially at how these terahertz give you 7 key features that are very important. One is this quasi-opticality of the band, which inherently enables sensing. Second is a new architecture where RISs and other aspects come into play. Third is a closer synergy between higher frequency bands and lower frequency band. 4 is actually doing sensing. So we're going to talk quite a bit today about this. And there's a lot of phi layer issues. I think many of you have done a lot of work there. And there's also spectrum access and, of course, real-time optimization. So today we're going to focus on joint sensing and communication and more along the lines of performance of architecture. And, of course, there are many applications, one being, I mean, extended reality, digital twins, and others. So let's start our technical part, right? So the question we're going to ask in the first and probably the longer part of the talk is, can terahertz provide high rate, highly reliable, low latency communication? And this is a recently accepted paper for VR or XR in the broader sense. So VR over terahertz channel. So terahertz for XR and VR in particular has the advantage of large bandwidth. So we're really good at getting, at getting high rates. And it has the advantage of at least being able to mitigate interference. I mean, it might not be eliminated, so we're going to use interference in our model, but at least you know that you can mitigate interference. The disadvantage, though, is the susceptibility to blockage, the molecular absorption, which actually limits the range, and essentially you can say that terahertz is, by essence, unreliable, right? So when we used to talk about reliable or HRLLC, that used to be, I mean, the thinking was mostly along the lines of sub-6 gigahertz, because we know millimeter wave and terahertz, they're unreliable. But here we have XR, which actually needs reliability. Again, maybe not as strict as HRLLC, but also needs high rates, right? So how can we reconcile the two? Terahertz offers an opportunity there, but we need to make sure that we leverage that opportunity by acknowledging that we have high bandwidth, but we also have some sort of unreliability that must be managed. So the question we're going to ask here is, what is the impact of this unreliable channel on my ability to achieve an immersive XR experience, right? So this is really the fundamental question. And this has not been studied. I mean, even by now, I haven't seen any work that looked really at this question, especially at Terahertz. So there has been a lot of work on HRLLC in the traditional sense. There has been quite a bit of work on Terahertz, I would say, on the physical layer sense, more along the lines of channel and green tracking and those kinds. But here we're looking more at the system and at a very particular and important aspect in terms of high rate, high reliability, and of course, low latency. So let's start with the system model. So consider an indoor, we're going to look at an indoor scenario where you have a dense deployment of small base stations using or serving VR users. We're going to use a MHCPP, basically hardcore process to model the deployment. So there's a small epsilon here, which allows you to kind of distance the base station. So we have densely deployed base stations in an indoor setting. And we assume that the computing of the VR is done at a Mac, which is equipped on the base station. And this has implication on our delay model that I will show later. Now, in terms of the interference, we assume that because the deployment is dense, there will be non-negligible interference within a radius of omega, capital omega, around each user. And this is considered, again, because we have a high dense network, because beam realignment problems for small or pencil beams can lead to interference eventually, right? So the interference model, while not being a contribution here, we used from an existing, a very well established existing work. We use this kind of Gaussian model, where you have the model of the interference, you have the mean and the variance that are completely characterized, and they're function of this region of non-negligible interference, of the epsilon that I got from this math and hardcore process, and of some of the traditional factors like the frequency and so on. So this is a very traditional or standard interference model. And next, the second impediment is blockage, right? So think about three impediments. One is interference, second is blockage, third is molecular absorption. So I'm going to go through them one by one. And blockage model has two angles. One is the self-blockage, so you can self-block yourself, right? And you can see this red user here within this yellow radius, he can self-block. But there's also dynamic blockage from others, right? Within this omega angle, he can have blocked base stations. And there's also the dynamic blockage from others. We assume that these other dynamic blockers arrive with a certain rate, right? So there's arrival rate of those dynamic blockers. So with that, we can find the probability of self-blockage, which is really just omega divided by 2 pi. It's really very simple. And then we can find the probability of dynamic blockage, which is function of these two, kappa and mu. So kappa is the arrival rate of the blockers. Mu is the departure rate of the blockers. You have the number of blocked base stations here and the dynamic blockage event. So we can now find the probability of being simultaneously blocked or being all line of sight links being blocked. And I mean, the math is simple here. You find this expression where you have the probability that an SBS is not self-blocked. And this is function of essentially the shape of the obstacles, right? So here we assume human shaped cylinders. So you have the heights, you have the velocity, you have the density of the blockers. Okay, so this is just a well-established geometric blockage model. So now for molecular absorption in the channel model itself, so this is again, there's still a need for more refined terahertz channel models, but we use this one, which has been again kind of widely adopted. There's this transmittance of the medium, and this, of course, the other factors, the speed of light and frequency. But what I'm interested in is this transmittance of the medium, which is function of this absorption coefficient. And this is very unique to terahertz. This absorption coefficient is what limits the range of terahertz, and it depends on the actually environment itself, the air in some sense, right? This is the molecular absorption. It depends whether you're indoor, outdoor, whether it's raining, whether it's humid or not. So this is really what we call the molecular absorption in terahertz. So now we have the instantaneous rate. Okay, so it's function of this transmittance of the medium. It's function of the kind of the constant parameters, A0, the power, the position of the users as well, and the bandwidth also. Okay, and R is the radius. So here N0 is this again is also function of the transmittance of the medium. So you can see molecular absorption appears kind of everywhere. So given that we're going to assume for this first model, the second one, I'm going to relax that assumption. But here we assume that since we are only looking at rate, we assume that the non-line of sight lengths are not useful. So the capacity is essentially the probability of line of sight multiplied by this capacity here. The probability of non-line of sight, assuming the capacity of non-line of sight is assumed to be 0. So now, given the blockage, what we want to actually characterize is the reliability in terms of the end-to-end delay. Okay, so from this blockage we can find the probability of line of sight, right? So this, I mean, essentially I'm trying to find this term P of lambda. So the probability of line of sight is function again of this region of non-negligible interference omega, of the speed of the blockers, and this is one of the first analytical results in this work. So the expression, it really captures how susceptible is your link to all these network parameters. You can see that an increase in the density of the blockers will significantly lower your line of sight. An increase in the region of the blockage or in the sector of the disk of the self-blockage will also increase significantly your line of sight. Will decrease your line of sight, increase the blockage, right? So that's what I wanted to say. So now reliability. I think the first question is more of existential question. So what is reliability, right? So what does it mean? So going back to reliability for us, it's a function of the end-to-end delay. So we need to find the end-to-end delay. So how does this VR system work? You have a VR user who will send some requests for VR images in the uplink. This work does not look at the uplink. So we assume this channel is reliable and it's fine. I mean, it works well. You don't need high rates here, of course. I mean, you just need to send simple inputs. And then the base station will have a MEC server who will queue these task requests in a queue Q1. Then this Q1 will enter the MEC server processor who takes these requests and processes and generates VR images that exit at Q2 here. They are actually buffered at the transceiver and transmitted over the channel. So terahertz essentially appears here in this region. So this is the terahertz link. This is what we're studying. So we're studying end-to-end from here, from all the way. I mean, again, we assume the uplink latency is not important. It's fine because it's short packets anyways. And then we go from here all the way back. This is where we're studying. So you have Q1, which is a computing queue, MM1, Q2, which is a communication queue, which is MG1, because the channel cannot be modeled as an MM1 queue. So now the existential question. According to 3GPP, and this is verbatim, reliability is the capability of transmitting a given amount of traffic within a predetermined time duration with high success probability. For us, this definition is necessary but not sufficient, because we need to I mean, this VR applications, they have this haptic, which is the kind of interaction with the medium, and visual experience, which they need a more refined definition of the reliability. This is essentially meaning you need to meet these requirements, you need to meet these latency and rate requirements together kind of instantaneously, right? Because if you're playing Star Wars, right, and if you're in a Star Wars universe, and all of a sudden you realize, no, you're in your garage, that ruins the entire experience. So even the slightest of disruptions to your immersive environment is not good, right? So you need something more stringent. So reliability analysis often relies on statistics, right? And we often look at different metrics. Many people like this value at risk, which is essentially a measure of risk in your distribution. And another important region is called the Rowan region, which is essentially the expected tail, right? The expected tail of the distribution. So average reliability, which has been around for a while, typically looks at either something like value at risk or like something like an actual average of the performance, which is not sufficient in an XR environment, because as I said, the slightest of delays, the slightest of disruptions can significantly impact your experience. I mean, think about, again, compare using watching a video and being in VR. If you're watching a video, if there's a little bit of buffering, you're okay, right? I mean, you're bothered and annoyed, but you're okay. If you're playing, again, an immersive experience, this becomes really not interesting, right? Because you're kind of going out of the virtual world. So we gotta look at the tail reliability during what we call extreme events. So extreme events could be a sudden blockage, a very strong deep fade, a change in the molecular absorption, all these factors that happen in a kind of a very extreme and rare cases. So we want to try to guarantee high reliability at the tail in an instantaneous manner with no instantaneous disruptions. So to assess the reliability at the tail, one can look at the one quantile value, right? But that does not give me a sufficient information, right? I mean, looking at the VAR, here in these two, they have the same VAR, but you can see the tail is different, right? So this single metric is not very useful. So instead, what we want, if you think about it, we want to assume the tail itself to be statistical and find the distribution of that tail, because that tells me a much richer view on how can my system sustain unreliable experiences or unreliable events, right? So the tail itself has a distribution, and it turns out that in statistics, there's something called the generalized extreme value theorem, which will allow us eventually, in a few slides, to actually derive the tail distribution. So essentially, this is what I want. What I want now, I translated my question, which is, can terahertz provide high rate, high reliable, low latency communication, into a very rigorous analytical question, which is, I have an end-to-end delay model that has computing delay, communication delay, that includes factors like blockage, stochastic factors like blockage, molecular absorption, and we need to make sure that the end-to-end delay is guaranteed at the tail. And so far, we need to find, so essentially, the fundamental question becomes, how do we find the distribution of the tail, essentially, right? And on top of that, to provide further guarantees, we use a concept called the tail value at risk, which essentially tells me that what is the confidence level of achieving a certain reliability metric, okay? It's kind of back-ended, or reliability is now further strengthened by using a confidence level through this concept of tail value at risk. Now, the analytical challenge itself is really to find the distribution of the tail. The TVAR is easy to find. You will see it's just a direct evaluation once you have that distribution. So to find the distribution, we need to characterize the moments. So we need the average anyway. So we find the first order moment, the mean of the end-to-end delay. You look at this, think it looks complex. It's not very complex. I'll tell you why. So this depends on very concrete network parameters. One is the service rate of the computing server. Second is the arrival rate at the computing server. Third is the utilization of your communication queue. And then you have the transmission delay. And this is where all things terahertz appear in this expected value of alpha here. So all things terahertz appear here. You can see kappa or K has appeared again. You can see the blockage parameters are appearing in the Z. You see the interference parameters are appearing. So everything appeared again. So the average end-to-end delay is equally influenced by the mean of the total waiting time for computing, the utilization of the channel, the utilization of the Q2, and the mean of the transmission delay. Keep in mind, the waiting time in Q1 is essentially influenced by the number of requests. It's beyond the control of our wireless network. So this is what the users are requesting. And of course, the processing speed. Now, the transmission delay moment depends on the average blockage rate as well, and the average terahertz data rate, and I told you that already. Now we need to find the second order moment as well. So we can also find it in closed form. And having the first, again, it's function of the same parameters, so I'm not going to dwell too much on it. Having the first and the second moment, then we can derive the moments of the highest order, and using some mathematical theorems, we can find the tail distribution, okay, using expected extreme value theory and some other theories. So we can find in closed form the tail distribution here. You can see it in this figure, or in this equation, sorry. This is the worst case distribution over all possible randomness outcomes. So it's a really very rich characterization of the tail distribution. We can see that the tail distribution is centered around the mean, and that kind of makes sense. The variance is very much influenced by the three moments of the rate and how it's affected by the blockage environment as well. So now with this theorem, which is really the main goal, we can have a very concrete way to assess whether terahertz can provide end-to-end reliability. And it's very rigorous and concrete in the sense that I tell you exactly what is the reliability definition and how that is affected by all things wireless, all things terahertz in this case. So obtaining the tail and statistics, as I mentioned, we can also define a confidence level, and this is where the TVAR comes into play. So it allows me to quantify with what confidence level can I achieve a certain reliability metric, and that's why it's a superior risk measure. And this is a corollary, so it's very easy to find. Alpha C is really what's important here, is the confidence level. So I can achieve a reliability with a certain confidence level. You can see there's the end-to-end delay appearing here. Okay, the derivation here is again very simple. So considering the T-bar allows us to provide seamless experience with a certain confidence. Now we'll take a special case where, assuming there is no blockage, so line of sight is guaranteed. So think asymptotic case. Now in this case, you no longer need to find the tail distribution or the distribution of the tail, because in this case you can actually find directly the CDF of the end-to-end delay. So reliability can be defined directly here. You don't need to go through distribution. So we can find if line of sight is guaranteed, the end-to-end delay CDF can be found in closed form. So this is harder to prove or easier to prove than the tail distribution, but this is a very asymptotic case, right? We're assuming that you have this guaranteed line of sight, right? And then you can define the reliability as the probability of being below a threshold, and this is very tractable, of course. So we can see again, once again, just like we saw in the tail, we can see that transmission delay is dominant in determining the reliability, and molecular absorption will also impact significantly the reliability. So now let's play around with the simulations to see what we can conclude. So you can see this VR session. You have three figures. Figure A shows you the average end-to-end delay. Figure B shows you the instantaneous end-to-end delay, and figure C shows you the tail end-to-end delay. So the average end-to-end delay, as you can see from this figure, does not really, I mean, it's around the 10 or even below 10 milliseconds. It does not exceed 20 milliseconds. So given an average, many interesting VR application, this sounds reasonable, right? So if you are analyzing only the average end-to-end delay, you would say, well, great, terahertz gives me all I need. There's nothing else I need. But then when you remember that this is a haptic and visual experience, when you remember there's senses being transmitted, then you look at the instantaneous delay and you see that sometimes there are, these extreme events, like there's the 80 millisecond. Zooming in further on the tail, you can see the tail is around 50 milliseconds, right? So it's kind of it's the double of the average. So this means that this positive viewpoint given by the average is not great. For the instantaneous end-to-end delay, we can see that a single event disrupts the experience. The tail is telling me that, well, an extreme event will lead to at least 30 milliseconds. And that's not good, right? That's not good in a VR experience. So now looking at the T-VAR versus the confidence level, you can see that it's easy to guarantee delays of 30 milliseconds with a confidence level of 80%. But it's very difficult to keep a low end-to-end delay with a risk percentile around 90% here, right? So this is because there is this susceptibility to blockage, and of course the molecular absorption plays a role as well. Versus bandwidth, you can see that there's the T-VAR actually saturates. So one would think, I have a lot of bandwidth, let's just add bandwidth and things will sort things out. That is not the case here. So you can see the T-VAR does not go down significantly. Now looking at the delay versus bandwidth, you can see that, of course, more bandwidth reduces the transmission delay. So in blue and red, you can see the general case. The blue, of course, Q1 is not affected by bandwidth. This is a computing delay. What's interesting here is the difference between the red and the green. The red is the Q2 delay when there is a general case, and green is the Q2 delay when you have guaranteed line of sight. You can see that significant gains happen when you guarantee the line of sight. This is reflected directly in the reliability here, right? So similarly, compare red and green, or compare red and blue in this case. So red is reliability for guaranteed line of sight at 10 milliseconds, and blue is reliability for delta at 10 milliseconds without guaranteed line of sight. There is significant gap between the two. You can see the same at 20 milliseconds, of course, but 20 milliseconds is easier to achieve. So again, we can see that in presence of blockage, the reliability is limited between 70% to 96%. For a target delay of 10 milliseconds, it's 70. For a target delay of 20 milliseconds, it's around 96. Okay. So the guaranteed line of sight scenario, a bandwidth of 15 gigahertz can allow you to achieve 999 for 20 milliseconds. So the guaranteed line of sight seems to be critical, right? It seems to be very critical. Now we can look at the molecular absorption, see how it affects a lot to end-to-end delay if the line of sight is not guaranteed. If the line of sight is guaranteed, some things are smoother, even though they still vary with the molecular absorption coefficient. In terms of reliability, we see the same. Again, these two figures are always mirroring each other, so you can see the reliability has a similar trend versus the molecular absorption. Okay. So in summary, can terahertz provide high rate, reliable, low latency communication? Well, this is the conclusion. When it is necessary, while it is necessary to have high bandwidth for you to get this large rate, and it's necessary to operate at regions of low molecular absorption like indoors, extreme events still disrupt your user experience. And to improve that, you need to use something that guarantees line of sight availability. We've done that in a different work where we used RISs to show that that can work. And it is fundamental to look at the extreme events from a tail perspective as well. As I mentioned already, so even if the average is 20, the tail can be from 30 to 90. And after guaranteeing line of sight, you still have short communication range. You still have other challenges in terahertz. Now, since blockage plays a key role in determining your system, and since terahertz is a quasi-optical band, the next question we ask, can we use this quasi-opticality to actually map the blockage or sense the blockage, to actually create a map of the blockers in an indoor environment, again, with VR applications. So the next work, which is a recent ICC actually paper, where we looked at this joint sensing communication in terahertz networks. So consider, again, we used RIS because from our insights, we already know that RISs allow me to have a better line of sight, at least. We have an uplink system here. So it could have downlink, but our focus is on the uplink for now. I'll tell you in a moment why. We have an uplink system where there are RISs transmitting essentially or receiving from the VR users their transmission using terahertz bands and a MAC server like before. And each RIS is assumed to use a what we call the array of sub-array structure, right? You can see the sub-arrays on the figure here. So we have UXR users. They can be mobile, moving around in the room a lot and changing the orientation. And each user has a uniform linear array of 2 antennas, RRF chains. So if they are all active, there are U data signaling beams, and we use SCFDM because it's much better at terahertz band because it avoids it mitigates the high PAPR effect of other schemes. Now, why uplink? The idea here is that these RISs, when they receive a communication signal in the uplink, they can actually leverage that to understand the environment, and they can sense the blockage in the room and then use it later to do downlink, right? So this is kind of the key point here. So after processing the communication waveform, this is important. It is a communication waveform at the subcarrier K, at sub-array M. We get this, the uplink receive signal, right? What we want, I mean, this is traditional, I mean, just a classical uplink transmission. You can see the combining vector of the RISs, the uplink channel matrix, the Gaussian noise, and the signal transmitted, which has a digital pre-coding and the actual communication signal. The key for us is to use this communication signal, and I have to stress it again, it's a communication signal, which is just sending, I mean, we're just communicating with the base station or the RIS in a way to actually extract sensing information. So this is really the key challenge here. So from communications to sensing. So we want to construct a single realization for sensing the wireless environment. So we take T snapshots that are recorded by the RIS. Each has J uplink measurements. Okay, so you see the uplink measurements J here, and over a time period of T. So the T appears actually here. So we're trying to find, again, over a T period of time, we're trying to find essentially the angle of arrival, the angle of departure, the time of arrival, and this allows us to actually characterize the blockage. And you will see in a moment why later. So we need to find this theta, this phi, this tau in order to sense this, okay? And this snapshot can be collected either line of sight or non-line of sight, and this is another opportunity. So we said before that terahertz is unreliable, so it has a lot of non-line of sight, right, blockages. So before we said, oh, we're gonna discard those, right? What's the point of using a blocked signal whose capacity will be like 0.001? It's really nothing. Here, what we're saying is, no, you should think of non-line of sight as an opportunity in the following sense. If you have a non-line of sight signal, maybe communication-wise, you cannot do much, right? I mean, there's nothing you can do with communication. But sensing-wise, you can actually extract useful information. And this is what we're gonna show. So in line of sight, we have this channel gain, okay, which is the function of the carrier frequency, of the speed of light, of the distance between the XR user and the sub-array. And in this here, we can see that in line of sight condition, having this situation awareness we just need to estimate, as I mentioned before, AOD, AORA, and TOA, right? So this can be used, this link can be used, this line of sight link can be used jointly for communication and real-time tracking at the same time, right? Now, if it's non-line of sight, we have a similar equation, but we have a reflector coefficient here, R, right? So the distances still appear, and there's the distance between the blockage and the subarray, the distance between the user, U, and the blocker, right? So, and there's the reflection coefficient at the blockage, at the obstacle. And this reflection coefficient inside of it, there's another angle called the angle of incident signal to the reflector, this psi. So for non-line of sight, this signal is useless for communication, but it's useful for situational awareness. So we can get the non-line of sight link, and then instead of discarding it, we use it to track the user and gather information. Now you can see here, we're doing all this communication and sensing using the same spectrum, the same hardware, and the same waveform. We're not changing it, right? So there are a lot of works that use all different sensing or standalone sensing and communication. Here it's everything is integrated. So how can we solve this problem? For the sake of time, the solution, I'll do it qualitatively today. So we need to estimate these sensing parameters, line of sight or non-line of sight, from T snapshots. So existing estimation techniques that use pilot signals, they have a high overhead. And typically their goal is to estimate channel, not really to do sensing, right? And in terahertz, with the coherence time being small, this is kind of not very useful. There are other estimation methods. There's this very famous music approach. Unfortunately, it cannot estimate multiple parameters, and it does not really work with this AOSA structure, the array of sub-array structure of our system. There are other techniques like compressive sensing. They're called on-grid methods, but they are constrained by the grid within which they search, which increases complexity. Instead, what we use, and again, I'm not going to cover the math here, I'm just going to show the theorem, we use tensor decomposition, right? So we apply tensor decomposition to prove the following, that we can find the AOA, AOD, and TOA corresponding to a given path using this equation. You have a closed form estimation of these metrics, and based on the line of sight or non-line of sight, you can find the position of the user and the blocker, and you can estimate them from these parameters, from the setup geometry and the refractive index of the human skin. So based on these positions, we can create a map of the blockage, and I'm going to show you the map in the next slide. So again, remember, this is done with the same waveform, hardware, and spectrum. So I'm extracting sensing information from a purely communication signal. It's a purely communication signal. So you can see here this figure. It's a map of a room where we estimated the blockage. This one is with 7 gigahertz bandwidth. This one is 15 gigahertz, 15 gigahertz bandwidth. In this one, we are using the 275 gigahertz or 0.275 terahertz channel. And you can see a few things here. First, this is a room. You can see that actually the lower regions of blockage, this is the blockage score, which means the higher blockage score is a higher blockage. You can see that the middle of the room is the least crowded area, right? So it turns out that if you go in the middle of the room, you have more possibility to actually communicate with your, to communicate with the RIS. This is seen in both figures, but we see that if you increase the bandwidth, the resolution is much better. So you have a more granularity in determining the blockage. So the difference is really in this zoomed in figure. You see how granular this is, how much you can actually pinpoint the blockage. So you have really a map that gives you a continuous range of values of the blockage score, and we can know every point in this map, what is the blockage score and how good or bad your communication will be there, right? So it's a win-win situation by increasing bandwidth because you have a higher rate and you have a higher resolution, right? So this is something we want. What about reliability and spectral efficiency? So we can see them here. So again, the message here is using a communication signal, I am able to do this tracking. Keep in mind that if it's line of sight, I'm able to do communication as well. If it's non line of sight, I just gather information for future slots. So in terms of reliability here, you can see we compared with a lot of things. So the proposed approach is the red one. And let's take the cases. There's also low mobility and high mobility cases. So the highest gains we achieved are in a low mobility setup, right? Around 20% for 20 users in some sense, in terms of reliability. And in terms of the spectral efficiency, you can see we're very close to a standalone system. The difference is that we don't use, we're actually better than standalone system while we use a single hardware. And we're very close to the perfect CSI case, actually. This is what I want to say. We're pretty close to the perfect CSI case. And this is, as you can see, this is an ICC paper. It's an early work. We're working on extensions. but you can think of a lot of things, right? Using this information in a learning algorithm, doing better estimation, and extending it in so many directions. So finally, I'm going to conclude with an overview of our research and quick conclusion. So we've been working on different areas. I kind of talked about one bullet today, which is essentially terahertz, a little bit on XR, kind of around this sense. We're doing a lot of work recently on this semantic communication using generalizable AI in some sense. We've doing quite a bit of work on communication control for autonomous systems in general sense, and sensing and communication plays an interesting role here. We have a bit of threads on more like the ML side, doing continual learning, designing distributed multi-agent architectures, more on the energy efficiency and things of that sort. We have a project on age of information, which is also related to semantic information in different ways. We have a thread going on recently on quantum networks, more on the optimization and the use of quantum physics to design better quantum networks. And there are some other works, again, game theory, we've done quite a bit over the years, and we're still doing quite a bit there. And finally, in conclusion, XR is very rich for 6G, and XR in the broad sense, right? You can actually disconnect yourself from the actual application and just say there's high rate, high reliability. What can you do then? Right? And terahertz can give you the bandwidth, but it does not give you the reliability. So the message on terahertz is that we should, while we should continue understanding the physical layer, there are more interesting problems also coming up elsewhere. And sensing and communication is interesting. So you have a lot of confluence of different fields here. And finally, I'm happy to conclude and take questions.
Okay, thank you. Thank you very much, Walid, for the very informative presentation. Now you move to the Q&A section. So if any of the attendees have some questions, feel free to write in the chat box or to raise your hand and make the question by yourself. Okay. Actually, I went through your paper about 7 features of terahertz many times. This is a very good paper. I forwarded to many students. And I think one concern that we have when you're going to implement terahertz in 6G, it refers to the many impediments that may arise from its feature. I mean, the blockage, the molecular absorption, because I think the big promises of terahertz is this kind of integration, high rate communications and high resolution sensing capabilities. So, but do you think these impediments may disrupt and jeopardize these envisaged capabilities of terahertz? I mean, communication and sensing, especially if you look at a large scale. I mean, if you look at an outdoor scenario with a high mobility.
Yeah, so I think mobility is a big challenge, right? I don't see terahertz working for highly mobile users at the beginning, which is why if you look at our focus, it's an indoor kind of controlled environment where it makes a lot of sense to have terahertz, right? It's short range already, and that's a good way to start with it. Eventually, I think the 5 folks are getting much better at controlling the beams. And we're getting much better at controlling these impediments. So you can see like one example is the second work I presented, which is you have an online of sight link, and that's usually a wasted opportunity. Instead, we use it for sensing, right? Because sensing, in some sense, I think sensing in terahertz is kind of always available, right? If you have the right signal processing tools and machine learning as well, you can always extract some useful information there. Now, in terms of communication, I think, initially, again, probably controlled environment, either indoor or let's say these information showers that support or are synergistic with other frequencies. That's the only way for us to move forward, as opposed to just deploying. I think even millimeter wave now is not that working that well for mobile. I mean, real mobile vehicular kind of applications.
I think one good advantage of implementing terahertz is any kind of obstacle can be seen as a sensing opportunity. And I think
exactly. And that's what we tried to do. Yeah, that's what we tried to do in the last work. Essentially, I tried to stress that many times, which is this is a communication signal. We're really extracting it. We're not sending a specific signal for the sensor.
Yeah. Okay. We have a question
I can see.
From the audience. How do you see the feasibility of your work on a real experiment?
Okay, that's a great question. I think there's two angles to it. First, the first work is more performance analysis. So the first work is not the work that you take and put in the experiment. It's actually the reverse. When someone does an experiment and gives me a better channel model, or someone does an experiment and gives me a more accurate delay model, I can feed that back into my results and then update them. It's kind of like it's a continuous loop in the first work because it's a performance analysis, right? It's not an operational work. Now, the second work, I think initially, again, not to promise too much, one could start it with kind of existing maybe millimeter wave equipment and try to do some tensor decomposition or some sensing on that. I think you can start with a baby step. You cannot come and put it all together. I mean, in fact, I mean, we don't have yet terahertz base stations, but that does not prevent us from trying to analyze what we can achieve with those. I think there are hardware challenges, which I'm not an expert. But assuming the hardware challenges are overcome, again, in the first work, I need experiments to actually give me a better model. In the second work, then I hope we'd be able to deploy that approach along with some ML algorithm, which I didn't show today, to do that.
Okay, we have another question. I think it's closely related to my previous one. It's about a possibility in apply terahertz for outdoor scenarios, especially for drone communications.
I mean,
the short range.
Yeah, I've seen some works on drone, and we have a small work as well there. I think for drone, because of the ability of line of sight, despite the short range, that could still be good, especially if, I mean, there are regions in space, it depends how high you are, where you can kind of have a better control on the molecular absorption, right? There's some better ways to do it. But in the traditional outdoor, meaning like outdoor vehicular, as I mentioned to Daniel early on, I think that's still far off. I mean, I don't think terahertz can do much there. But it can do what it can do is being an information shower in the sense that you're moving along with sub 6 gigahertz or even millimeter wave. So you have a user moving and you find an opportunity to transmit a lot of data. Then you use terahertz. But most of the time that user is still using the more reliable and the more controllable, let's say, not reliable, the more controllable bands.
Okay.
I just saw the comment on the outdoor backhauling. I think, there are many experiments going on there. I agree.
Okay, any more questions? Yeah, regarding the machine learning algorithms that are feasible for being applied for terahertz, especially because terahertz channels has a highly vary network. I mean, the coherence time is extremely short. It may become the currently machine learning algorithms, which are based on online fashion, maybe unfeasible, right? Could you please elaborate about it? I mean, how can you deal with this real-time configuration when considering terahertz channels?
That's a great question. I don't think it's really just terahertz. It's really everywhere, right? Machine learning, and that could have been for the talk today, but I think Merwan said 6G and kind of communication, so I went to the communication side. So in ML, we've been doing, and we're actively working a lot on what you can think of as reliable low latency learning, not reliable low latency communication, in the sense that can we cut the communication or the time needed to train? Can we actually make the machine learning algorithm more efficient at processing the data, more faster? I mean, some people call it reasoning, even though that's it's a very loose term and many people don't know what it actually means. I'd rather say it's more generalizable ML, meaning I can see something and actually repeat it again, and do better in a different task. So kind of learning bit by bit. Some tools there, like curriculum learning, like meta learning, allows me to do that. But they have to be tailored to wireless, meaning like what the task is for machine learning is not what the task is for us. And there's quite a bit of interesting work to be done there. I think for us, we should think more how to re-architect machine learning algorithms to actually instill in them, one, reliability, meaning that they can handle extreme events. And we have a work there where what we did is really a data augmentation approach, but it's an interesting one. What we said is that, okay, RL algorithms specifically are often trained offline. But if they're trained offline, you have very little data actually to train them on. So if there's an extreme event, again, there's going to be a very low training time, and that's terrible online. So what we do is we add a GAN in the training, which allows me to add even more data. And that's done in a strategic way, in a refined way. And it allows you to kind of give, we call it experience deep learning. Give this deep RL more experience in things that he has not seen. So this is one approach. The other approach is along the side of meta learning. So you kind of allow it to instead of learning a task, you learn a class of tasks. Again, some people call it reasoning, but again, that's a very loose term that means a lot of things. I think that's a big challenge. I don't think there's a lot of, we've had a few works, there's a few works coming up, but I think it's a very interesting area. Again, that relates also to semantic communication, even though it's a different story, but there's a connection in this idea of eliminating training in some sense.
Okay, we have one more question.
Yeah.
It's about what are the VR content parameters taken into account for your simulation use case?
Yeah.
Video resolution, and can terahertz be useful for video streaming?
So I don't remember the exact parameters we had, but we only need, I think, for this one particularly. So for the second work, it's sensing, so we don't really need the type of content doesn't matter for us. It's really very physical layer. And the first one, I don't think I have the slide on the parameters, but I remember we got some. We had an example, I think, from Oculus or something. There was some parameters for the video resolution. It does not affect, again. Our approach is a little bit agnostic to the application in the sense that we don't really need to know the exact. It works for anything because just plug those into the equations. Now, can it be useful for video streaming? Yes, if you need the rate. So again, I'd always say that if there's something you can do with millimeter wave, then do it with millimeter wave. Right? We have better control. It works well. We understand it better. There's no need to use terahertz if it just you don't need it. Okay. I think, Carlos, I think he has a follow-up question.
Yeah.
Did you achieve it to include the communication network? Yes. So the latency parameters, I think that the target latency is a byproduct of the parameter. In some sense, we have the data rate, the power of I think which was minus 30 dBm, the power of the base station. So these are standard parameters that we took into account from wireless, right? So I think that the wireless parameters are pretty standard. We don't. The frequency is these results. The results on the slide now are for 1 terahertz. In the paper, we have also results for the 200 gigahertz as well. So you can do any, and the results are the same actually. The trends are the same. The actual numbers are different. So I don't remember what was the latency we achieved in the 200 gigahertz, but here we have a 20 milliseconds. And that's based on the network setting. Yeah.
Okay, we have another question about the hardware limitations. What are the theoretical challenges that I still need to be addressed as part of the research?
I think this is a broad question. I think one theoretical challenge is the one we discussed early on the learning side, right? So cutting the latency, cutting the training time there. Another one is on understanding if you want, the signal properties, the data structure, right? Because when you do sensing, I need to understand the structure of the information signal I'm getting. And we use tensors, but there could be better ways to do it. I think that's another big one. And there's quite a bit of optimization challenges. I did not talk much about optimization today. I didn't have time, but I think that's another area where there's a lot of interesting theoretical questions. And doing optimization with a highly dynamic environment, where some of it is stochastic, some of it is data driven, it's not easy.
Okay, thank you.